This demonstration looks at a Kامsól model of a MEMS-based energy harvester. This small component, only about 1 millimeter in length, could be used in arrays to harvest and recycle waste thermal energy in a number of applications. Here's an animation of the component in action. The rainbow contour map shows temperature in degrees Celsius. The displacement is magnified 1,000 times for visualization purposes, and the results are animated in time. So what drives the motion of this little device? Well, this component bounces up and down due to the fact that the strip is composed of 2 layers of different materials and is being put into contact with a heat source, here. The 2 materials, aluminum on top and silicon dioxide on the bottom, have different coefficients of thermal expansion. Strips like this, also known as bimaterials, bend when they are heated due to differential thermal expansion in the layers. When the tip of the strip is in contact with the heat source, it heats up via conduction and almost instantaneously bends away from the heat source. Then, as soon as the strip separates from the heat source, it starts to cool and therefore starts to recover the elastic strain caused by the differential thermal expansion. This happens until all strain is recovered and the cantilever returns to its initial undeformed configuration, at which point the heat source reheats the cantilever and the cycle repeats. This particular concept model cycles at a frequency of about 40 Hertz, which you wouldn't be able to see in real time, so I'm showing this video at 2 different slower speeds. The first speed is about 20 times slower than the actual speed, and the second speed is about 80 times slower. Notice the tip of the strip turning red as soon as it comes in contact with the heat source. Then immediately the heat starts to dissipate, causing the cantilever to bend back into contact. How quickly the heat is able to dissipate in the cantilever is the primary driver for the frequency at which the system operates. Though it's not being modeled here, the energy from the repeated thermal cycling in the cantilever can be converted to electricity by taking advantage of the pyroelectric effect. This concept model takes advantage of Kامsól multiphysics' ability to couple together multiple physical phenomena into one simulation. We solve both the solid mechanics equations with thermal expansion and contact, as well as the heat transfer equations. Additionally, the simulation includes pressure-dependent thermal properties in the region local to the contact. Let's take a few moments to look at how this model was set up. The first thing that I would like to show relates to building the geometry. And when it comes to modeling contact problems in Kامsól, it's important to know the difference between form union and form assembly. Down here at the bottom, the last node in the sequence here, we have the finalized node, which says form assembly. And this is actually not the default setting. This was changed from form union to form assembly. So form union will treat the objects as if they're welded together. Form assembly duplicates any shared boundaries. Now let's talk about the physics setup. For this problem, as was mentioned before, we are coupling together 2 physical phenomena, the solid mechanics and the heat transfer. And these the settings for each of these physics are found underneath the 2 nodes here. So firstly, we'll talk about the solid mechanics equations. Let's expand this node, and we can see that we'll be solving a linear elastic material model for all domains. And then if you expand that, you can see that there's a thermal expansion set to the strip, and this is where the coupling is defined between the solid mechanics equations and the heat transfer and solids equations. Here, the temperature field, denoted by capital T, is read in from the heat transfer and solids solution, so that the heat transfer and solid temperature field is what drives the thermal expansion in the strip. The second node here is the free node. This is the default boundary condition, and it's overridden in 2 places by this fixed constraint condition, which will set the displacement equal to 0. Over here on the left end of the cantilever strip, and then at the top of the heat source, the displacements are set to 0 there. So that will constrain all of our rigid body modes for this problem. The next node that I'd like to talk about is this contact node. Here's where we define the mechanical contact between the heat source and the strip. The last node that I'd like to talk about is this point load node, and this defines a force F0 in the positive y direction acting on the end of our strip. And this parameter F0, back up under global definitions, you can see is defined as 2.5 E minus 3 newtons. And the description here, what I'm calling an electrostatic point force. This is a relatively small but necessary force applied to the end of the strip to model the effect of an electrostatic force in the real system, which is used to hold the strip against the heat source just long enough for it to heat up before the bending force from the differential thermal expansion overcomes the electrostatic force and the strip breaks away from the heat source. Without this force, the material bends away too quickly and the energy harvester sacrifices efficiency. Let's move on to talk about the heat transfer and solids equations. The heat transfer equations are solved in all domains. The default thermal insulation condition is applied to these boundaries and overridden on the left end of the cantilever beam by this T cold temperature condition, which is set to 20 degrees Celsius. And there's a T hot condition set to the upper boundary of the heat source. And this is set to 170 degrees Celsius. And then finally, probably the most interesting node in this model, there are a number of different settings. You can have different constriction conductance correlation models, either the Cooper-Mikic-Jovanovic correlation or the Mikic elastic correlation, as well as a user-defined correlation. You can set a gap conductance correlation. And then here under the context surface properties, we can set the surface roughness properties. And then here under contact pressure, here's where we've coupled the solution to the solid mechanics equations into the solution for the heat transfer and solids equations. And so now we have a bidirectional coupling where the solution to the solid mechanics contact problem is actually affecting the thermal properties in the local region where the contact happens. Okay, now that we've completely defined our finite element problem, we need to solve. And solving in Kامsól is done under this study node. On step 1, time dependent, we can see that we're solving for a range of times from 0 to 0.1 seconds. With a time step of 5e minus 5 seconds, so relatively small time steps. And this is going to give us about 4 cycles worth of the operation of this system. Okay, once you have a solution, the solution is stored under the results node, and you can post-process those data sets with many different types of post-processing operations and visualization techniques in Kامsól. I have generated a plot that shows the tip displacement and tip temperature on one plot. And you can see that as the tip, right from the beginning, begins to heat up, that as the temperature rises, that the tip begins to, the displacement begins to drop. And then as the material cools, it bends back into contact, and the cycle repeats over and over at a rate of about 40 hertz. This concludes this demonstration. Thank you.